Ladies and gentlemen, today we are presenting our study on ceramic filters for the efficient removal of azo dyes and pathogens in water. I am Miss N.K. Ngubeni, and my team members presenting with me today will be Shange N.A., Lamini L., Anna U., and Mabusela M. Access to safe drinking water remains one of the most urgent global challenges of the 21st century. Despite water covering over 70% of our planet, less than 1% is available as safe potable water. Industrial activities such as textile manufacturing, agriculture, mining, and energy production continuously introduce pollutants, including pesticides, heavy metals, detergents, and synthetic dyes into our water systems. This issue is particularly severe in low-income countries, where the lack of centralized water treatment facilities result in significant public health issues. According to the World Health Organization, more than 500,000 children die every year from waterborne diseases, and over 99% of these deaths occur in low-income regions. Clearly, affordable and effective water treatment solutions are essential. The problem this study addresses is twofold. 1. Chemical pollution. Azo dyes such as methylene blue and o-toluidine blue are widely used in industries but are resistant to natural degradation. They persist in the environment and pose genotoxic, mutagenic, and even carcinogenic risks to human health. Number 2 will be microbial contamination. Contaminated water is often a carrier of dangerous pathogens, including Staphylococcus aureus and S. typhi, leading to diseases like cholera, dysentery, and typhoid. Traditional water treatment methods like reverse osmosis and ultrafiltration can remove these contaminants, but they are expensive, energy intensive, and not always accessible to rural or low-income communities. Therefore, there is a clear need for a low-cost, sustainable, and a point-of-use solution that can both remove chemical dyes and harmful microorganisms from contaminated water. This is where ceramic filters made from locally sourced clay and bio-waste offer a promising alternative.
I am Ms. Shang N.A. and I'm going to talk about aims and objectives. The main aim is to develop and evaluate low-cost ceramic filters for removing dyes and pathogens from water. And then when it comes to objectives, is to fabricate ceramic filters using clay plus coffee waste, is to characterize filters, porosity, surface charge, etc. Is to test dye removal, MB, OTB, and to test pathogens removal, S. aureus, S. typhi, and to evaluate reusability. And then we have this diagram. So this diagram is a schematic illustration of how a ceramic water filter works for removing azo dyes and pathogen. So this cylinder represents the porous ceramic filter. The contaminated water with azo dye molecules and pathogens like bacteria or viruses that are shown as red and brown particles, they enter from the top. The pores of the ceramic material act like a fire sieve, physically trapping the dye molecules and microorganisms. The blue line or arrow shows the flow of water as it passes through the ceramic. And then at the bottom, there is a clean filtered water emerging.
Ceramic filters are made up from a mixture of clay and coffee bean residues. Water is then added in small portions to this mixture, and it is then mixed to form a smooth dough. The addition of water promotes homogeneity of the mixture. The dough is then put in a custom-made wooden mold and is then compressed to produce uniformly shaped wet ceramic filters. These ceramic filters are then dried using the temperature of the surrounding environment for 7 days. After the 7 days of drying with the surrounding environment temperature for 2 hours, they were heated in a muffle furnace at 600 degrees Celsius at a heating rate of 20 degrees Celsius per minute. Afterwards, the ceramic filters are put on an incline, were then put on an incline to 90 degrees Celsius for 4 hours. We are now going to look at the characteristics of the feedstock and ceramic filters. This investigation will be done using the leftovers of clay and coffee bean residues that are dried to investigate their surface functional group, their crystallinity, surface morphology, elemental composition, and thermal stability. Using a Fourier transform infrared spectrometer, the infrared spectra of coffee bean residues, clay, and ceramic filters were collected for before and after filtration in a wave number range of 400 to 4,000 per centimeters. The crystallinity was analyzed using an X-ray diffractor operated at 40 kV and 40 mH with a monochromatic radiation at wavelength of 1,5406 meters. The surface morphology and elemental composition were coupled together to an energy dispersive X-ray spectrometer in a field of emission mode under a vacuum of 9,634 times 10 to the power negative 5 pascals. The BET analysis measured the surface area and the pore size, and also the DTA tested the thermal stability. Now, the amount of ceramic filters needed to remove the cationic dyes, which are methylene blue and o-toluidine blue, were assessed under the following procedures. 80 milligrams of each of the dye was transferred to a 400 milliliters volumetric flask, then was diluted to 400 milliliters with deionized water. Each dye was then filtered through the ceramic filters, and the permeate was collected in an interval of 2 minutes. Then it was done 4 times for methylene blue and 5 times for o-toluidine blue. The stability of ceramic filters was determined by using recyclability tests. After each filtration process, the ceramic filters were washed with deionized water various times and then dried in an oven at 120 degrees for 4 hours. Before the next cycle, the ceramic filters are then heated at 500 degrees Celsius in a muffle furnace. 4 cycles are required for MB and 5 cycles are required for o-toluidine.
Results and discussion. We have 3 types of surface functional group, of which is clay and then coffee bean and ceramic filters. Under clay, the graph stretches between 3,600 and then 3,100. Under coffee, the graph stretches between 3,400 and 3,000 per centimeter. Under ceramic filters, the pair contains 2 material, of which is OH and CF. We then have removal of pathogens. CF25 and CF30 removed 100% of bacteria. CF35 and CF40 showed lower removal initially but improved after dilution. Low porosity filter is equals to better bacteria removal, while high porosity, they are less effective due to fast flow. Clay mainly contains 60% of potassium oxide and magnesium oxide. Under texture properties, CF between 25 and 35, the peg is 6.2 to 7.9 meter. CF 40, of which the peg is much higher, it is 35.3. CF then shows the heterogeneous surface. Under thermal stability, mass losses between 35 to 57 from 50 degrees Celsius to 850 degrees Celsius. Major mass losses below 400 degrees Celsius from moisture to organic material combination. Kelonite dehydroxylation to metakelonite at 550 to 650 degrees Celsius. Very little weight loss above 540 degrees Celsius. Under results and discussion, we have three types of surface functional group, of which is clay, coffee bean, and ceramic filters. Under clay, the hydroxyl peg show it is between 3,600 and 3,100. Under filtration performance, we have removal of methylene blue. Removal efficiency increases over time. MB removal, it is between 42.99% to 59.7%. OB removal, it is between 79.95% to 92.72%. High flow of CF40 removed dies more slowly. Under surface change, CF have a negative zeta potential. Negative charge is due to isomorphic substitution in kaolinite structure.
In conclusion, in this study, we successfully developed low-cost ceramic filters made from clay and coffee waste. These filters remove up to 92% of methylene blue, nearly 60% of toluidine, and up to 100% of harmful bacteria. We also found that increasing the coffee leftovers improve porosity and flow rate. Importantly, these filters can be reused at least 4 times without losing performance. And unlike silver-based filters, they carry no risk of metal leaching because they are made from local available, inexpensive materials. These ceramic filters are practical, sustainable, and affordable solution for communities without access to centralized water treatment.